Hello, are you able to see the slides?
Yes, sir.
I am changing them. Just confirm you are seeing the change. I am changing
Yes,
the
sir.
slide. You are seeing?
Yes, sir.
Okay, good. Okay. Welcome to Department of Chemical Engineering, Banastali Vidyapeeth. We are on THE 305 Chemical Technology lecture number 23. See, in the last lecture, we got into the exciting world of petroleum industry. Petroleum industry is a standalone by itself. It's a giant by itself. You can put oil industry on one side and all the remaining chemical industries on the other side. It's like that. Then, in the oil industry, we have three big terms which come up: upstream, midstream, and downstream. Upstream is also exploration and production. Midstream is transporting it from the drilling place to the refining place. And downstream is where the actual refining of the crude with unfinished products ends up as finished products. So that is upstream, midstream, downstream. In upstream, to understand the exploration, we need to get an idea of the origin of petroleum, where we saw it is by two contradicting theories, abiogenic and biogenic. But finally, biogenic is what is more accepted, even though abiogenic, there is some possibility some oil was formed due to some reactions in the earth which has nothing to do with biological material. But by and large, it is accepted that biogenic material, organic, plant, animal waste, they got decayed, and initially they formed what is known as kerosene, which is a type of a very crude liquid. And then, it went through diagenesis, catagenesis, metagenesis at different temperatures below 60 degrees, then 60 degrees to 170, 150 degrees, then 200 degrees metagenesis, where different stages of the hydrocarbon formation took place. Okay, so then there's a source rock where the oil is formed, and when it gets expelled from the source rock, then it goes through the porous rocks and travels. Oil and coal have similar origin, but coal stayed where it was formed, but oil did not stay where it was formed. Oil, being a liquid, could move through the pores of the rocks until a place where it could hang around and get held up came. The reservoir, where you have a rock, which covers the top of the reservoir like a lid for a bottle, right? So that is how the oil got trapped, right? And we use many exploration methods, geological and geophysical. The geological methods include analysis of the rock samples, flora and fauna of the likely place where oil is to be found. And the geophysical methods include gravimetric, where we do very intricate gravity measurement to see if there is a difference in the gravity value at that place or not, and magnetometric, and what else? Then electrical conductivity in association with magnetic method, and seismic method, where we actually place small, explosives like a dynamite stick in different parts of the site, and see the propagation of the sound waves and measure it. And the propagation of the sound waves through a reservoir where oil exists and where a reservoir where oil does not exist, they will be distinct. So seismic is one of the very crucial study, a method in the geophysical for finding the water. It is just not data, it is a lot of analysis, computer modeling. Supercomputers are used for simulating the whole set of data to find out what is the extent and quantity of the origin. I mean, how much quantity of petroleum, how much the reserve contains, it's all calculated. Okay, that is about the, and then you put a drill, the test drill, and then final drill, and the drilling. And once the well is exhausted, you have to abandon the well. There is a lot of procedures for it, right? Then we saw the composition of crude oil. By and large, we found the distribution of carbon, hydrogen, nitrogen, oxygen, sulfur, etc., is in a very close range, right? So based on the composition, I mean, chemical element, it's very difficult to classify the crude. So we base it based on whether it is a paraffinic crude, naphthenic crude, or aromatic crude, right? So you know, paraffin, CnH2n plus 2, and olefins is CnH2n, and the naphthene or CN, what is that, H2n, right? That is the cyclohexane, right? C6H12. Then the aromatic, benzene, C6H6, CnHn, right? So based on this, we found 6 classification: paraffinic crude, naphthenic crude, paraffinic, naphthenic, paraffinic, aromatic, etc. Right? And based on the API gravity, we can measure, classify the crude into extra heavy, heavy, medium, and light, or based on the density of the crude, based on wax content, based on sulfur content. Whole lot of parameters are there: viscosity, pour point, nitrogen content, salt content, right? All these are put in a like a what do you call a health examination type. The crude assay is taken out to decide the strategy for refining, and that is about the crude classification and composition, right? Then the crude enters into the refinery, that is a downstream operation. So yesterday we had a whole focus on the upstream operation, and also we had a glance of how the crude oil pricing is done based on whether it is a light crude. Light crudes are the most preferred, remember. And what is that? The light crude is based on the API value, and sweet crude or sour crude. Sweet crude means it contains less sulfur. Sour crude means it contains more sulfur. More sulfur means more headache, right? So because sulfur is poison for many of the catalysts that is used in the refining operation. That's the problem. Okay, so these are the things which we had a look in the last lecture, and then we saw how the crude pricing is done based on the light crude sulfur content and the API value, and also 2 benchmark crudes. That is the West Texas Intermediate, that is known as the WTI, which is from USA, North America, and Brent crude. Brent crude is from Europe, from the North Sea. North Sea is actually a cluster of several countries drilling in the North Sea, some England, Norway, Sweden, etc. So Brent is the common name given for the North Sea crude oil. Based on these 2 benchmarks, all the pricing of crude is done, right? So we now move over into the downstream operation, and there we start our lecture today, right? Downstream is a term, right? Downstream is a term which is used in the oil industry for refining, and the purpose of refining, what is the purpose of refining? To transform the various kind of crude oil into finished product that meet certain precise specification, not any arbitrary. In short, downstream is starting with crude oil containing unfinished products and refine it in a whole lot of operation and get the finished product. So crude oil, unfinished product, containing unfinished product, go through refining and comes out as finished product. So this is in a nutshell what is downstream, right? The range and quality of refined petroleum product, that is the how much product we get and what quality we get will all depend upon the type of crude oil used as feedstock and the configuration of the refinery. Remember, the refinery may include certain operation, may not include certain operation, because crude to crude, the properties differ, right? So remember that this point should be kept in mind. Light and sweet crudes are more expensive and generate greater yields of higher value refined petroleum product. Told you light crude and sweet crude. Sweet crude means having less sulfur. Light crude is the one with the API value, I think about 50 or something. Just check that up from the last lecture. Okay, so you get good quality petroleum product, gasoline, diesel, aviation fuel, if my crude is light and sweet, right? Heavier and more sour crude are less expensive, they cost less, but generate greater yields of lower value petroleum products such as fuel oil. So light and sweet crude will give me more up-end lighter hydrocarbon, whereas my heavier and sour crude will give me, they are less expensive, but they will give me more yields of lower value products like fuel oil, etc. Right? The configuration of refineries is typically oriented toward, most refinery is oriented for production of gasoline, that is petrol, right? What you get in the petrol pump, that is gasoline or petrol, where the configuration of others is oriented toward production of middle distillates, such as this diesel fuel and aviation. So some crudes may focus more on the gasoline, some refineries may focus more on optimizing the petrol production, whereas some may focus on the optimization of the diesel and aviation fuels. Let's look at one diagram to begin with. There are 1, 2, 3, 4 main operations in the refinery. The first one is atmospheric distillation, right? And it separates the crude oil into broadly naphtha, light oil, and heavy oil. Then the second operation is the residue, atmospheric residue, that is the bottom of the atmospheric distillation column is known as atmospheric residue. That is the input to the vacuum distillation column. So this one is your atmospheric distillation column. In the petroleum industry, it is also known as the topping column, right? Topping column means and this is known as vacuum distillation. This is also ADU, atmospheric distillation unit, and vacuum distillation unit is referred as VDU, vacuum distillation unit. Then the third main operation is heavy oils are cracked into usable products using several processes. I have a whole lot of, processes, catalytic mainly, by which I can convert my heavier products into lighter products. Remember, the lighter product, that is the lower boiling hydrocarbons, have more market value than the higher boiling one. Remember, fuel oil is cheap as compared to petrol or diesel, right? So, because fuel oil contains heavier hydrocarbons, whereas diesel and petrol contain lighter hydrocarbons, right? So, but the heavy oils can be using unit processes cracked, meaning I can break a long chain hydrocarbon into small pieces and increase the lighter products, right? So this whole complex is a set of, catalytic operation. I may do catalytic cracking. I may do reforming. That is, my aromatics are less, and I can convert the paraffins into naphthalene and naphthalene into aromatics, like hexane can be made into cyclohexane, which is a naphthalene ring compound, and cyclohexane can be dehydrogenated to form benzene, right? That is aromatization, right? So all this is happening here, cracking, reforming, right? Alkylation, isomerization. There is a whole lot of catalytic operation. In addition, there are many physical operations. Physical operations already you have seen atmospheric distillation, vacuum distillation, then solvent extraction is done to remove certain unwanted compounds, right? So you have in the refinery catalytic processes, physical processes where physical change is happening, like solvent extraction, distillation, etc., and thermal operation, where using heat, chemical changes are happening. And when we do the changes with catalyst, we call it catalyst-based chemical changes. So thermal-based chemical changes and catalyst-based chemical changes. So this figure is just a big one, and many products form, they are all taken and blended, right, to form your required product, right? For example, the actual petrol you get may be a mix of something from the atmospheric column, something from the cracking column, something from the reforming column, something from the isomerization, something from the alkylation, all mixed up, blended, you get your blend, right? So, because there are many requirements which cannot be met by just one, branch of the one set of product. So, different products have different properties. So, in required quantity, they'll be taken and blended to form. Already we have seen the global top 10 oil companies: China Petroleum, China National Petroleum, PetroChina. Top 3 by sales are in Chinese companies. Then comes Royal Dutch Shell, Saudi Arabian, BP, British Petroleum, Exxon Mobil, Total, Chevron, and Rosenfeld. Right. The Indian oil and gas companies include Indian Oil Corporation, IOCL, ONGC, Bharat Petroleum, Reliance Petroleum, SR Oil, right, Cain India, Gas Authority of India, GAIL, Hindustan Petroleum, HPCL, Oil India, OIL, and Tata Petrodyne. These are some of the big names in the Indian oil industry. These are the global ones based on sales. Now, petroleum refining technology. How the crude oil, just see this figure, how the crude oil with containing unfinished product ends up with finished product, right? So this box is what we are going to break through now. So an overview of the oil refinery is increasingly complex. They constitute a relatively mature and highly integrated industrial sector. So refinery is industry by itself, right? Besides physical processes such as distillation and extraction, large number of chemical processes are applied, many of which are catalytic. This is what I was telling you, right? There are physical operation, there are chemical operation. In the chemical one, some are by heat, some are by catalyst. And the reason that such a complex set of process is needed, why do we need such a complex operation? Because the property of the crude oil delivered and the property of the product wanted, they are vast different. So to reach the product specification, we have no option but to carry out all these operations. Especially for fuels in the transport sector, extensive processing is required in order to obtain product with satisfactory performance. See, the fuel for the aeroplane, the fuel for the car, the fuel for the truck, right? So these all have different properties, right? So since they have precise specifications, we need to carry out so many operations to reach the desired specification. Another reason is environmental considerations. Okay, legislation calls for increasingly cleaner processes and products. So, oil industry is considered as one of the villains for environmental cleanliness. Right. So there are a lot of rules and regulations. So to obey them, I have to incorporate so many checks in the refinery, which makes it more complex. Right. In fact, at present, legislation related to minimizing the environmental impact is a major drive for process improvement the development of novel processes. So it is an environmental requirement which is bringing about many modifications and changes. For example, a whole lot of H2S is produced in different parts of the refinery. H2S, we put it in the class process, which we have seen in the sulfuric acid manufacture. H2S is the input to make elemental sulfur, right? So, a lot of operations are there in petroleum refining just to meet the environmental requirements. So, I'll show you a figure where this diagram is gives you, right? Remember, the first thing in refining is the crude must be desalted and dehydrated, right? Dehydration means removal of water. Desalting means removal of salt. It's obvious why salt must be removed. Because if salt is present, it is going to form scales in the refinery and reduce the heat transfer, right, and spoil the equipment. So salt in the crude must be removed before the refining starts. And any water content in the crude oil, because there will be some quantity of water, right? After all, down the oil well, there is some quantity of water is going to be there, and we have to remove the water because your heat requirement in the refinery will go up to drive away this water, right? So desalting and dehydration is precisely the very first step in the refining operation. Then it goes for atmospheric distillation and then vacuum distillation, etc. Right, we'll come to the figure. Right, the distilled fraction cannot be used directly in the market. Remember, just because you have done atmospheric distillation and vacuum distillation, it doesn't mean your products are ready, because they may not be meeting the specifications of the product, right? So I need to carry out many more operations before I can reach the required specification of the product, right? See, for petrol, it is just not to drive the car. It has an octane number, viscosity, pour point, so many things have to be met, right? So in subsequent discussion, most of the processes in this figure we will be discussing, and they are divided into physical and chemical processes as shown in this table, physical processes and chemical processes, right? And oil refineries show large difference, and besides the processes mentioned here, many others are applied, right? For example, the figure which we are going to see, right? The figure which you are going to see, they don't show processes for treating refinery off gases. That is how we treat the exhaust gases from the refinery, and sulfur recovery, class process. These are not shown, and water treatment, right? Wastewater treatment. These are not shown in the refinery diagram, but they all exist. It will make it more complex. Just have a look. Desalted crude oil go through atmospheric distillation column, right? And you form LPG and gas. This is called straight run gasoline or light naphtha. Then this is naphtha, also called heavy naphtha. Then middle distillates. Middle distillates could be diesel, etc. And heavy atmospheric gas oil, right? So first look at it. These are the fractions which come from the atmospheric distillation column. Then the bottom product of atmospheric distillation goes into vacuum distillation, from where I get vacuum gas oil and a set of product called as lube base stock. This means they are the base stock for making lubricating oil. That is a extract cut from the vacuum distillation column. Then the bottom of vacuum distillation, bottom product of vacuum distillation, see the bottom product of atmospheric distillation is a feed to vacuum distillation. And the bottom product of vacuum distillation may go for propane deasphalting, that is to remove any asphalt content in the distillate using propane as a solvent. Propane absorbs the solvent and the liquid is removed, right? And or the bottom product may go for thermal treatment. The delayed coker, flexi coker, these are thermal processes, right? And from where, again, one product I get is coke, that is like equivalent to the, see, remember, in coal technologies, we saw that we put coal into an oven and end up getting coke. In the same way, this coking column will result in the formation of coke. And the gaseous products, they are all taken for subsequent treatment. And some product may have very high viscosity. I may use what is known as vis breaker. Vis breaker is viscosity breaker, right? To reduce the viscosity. You know well that, by applying heat, the viscosity will be reduced. Example, the coconut oil freezes in winter and you put it in a bowl of hot water, it melts. That is it goes back to liquid. The viscosity is now improved, right? So similarly, some products go for some more solvent extraction. For example, the lubricating oil cannot have cyclic compounds and aromatic compound because they have undesirable properties. So I will have to remove deasphalting propane as solvent. Then I will use some solvent extraction for removal of aromatics, which are not desirable in the lube oil. And then wax is not desirable in the lubricating oil, because remember, if wax is there, when you use the lube oil, if wax content is there, then the wax will clog the machinery, right? So wax must be removed. And we typically remove the wax using some solvent extraction process. So remember that this whole bottom half is full of solvent extraction. Propane deasphalting, aromatic solvent extraction, solvent dewaxing, right? And I get a whole range of products, right, from which is there in my pool, and I blend the required way to get my products. Okay, so this is about it. Now come to a table where we have whatever we have seen here, various operations, I put it in a tabular form. Physical process, chemical process. Physical processes are desalting, dehydration, removal of water, removal of salt, then distillation, which is both atmospheric and vacuum, then solvent extraction like propane deasphalting, solvent dewaxing, then blending operation. Blending is mixing to of different proportion to get the desired product. Then in chemical process, I have thermal and catalytic. Under thermal, I have vis breaking, or it is a short form of viscosity breaking. Delayed cooking, which is actually when I apply the thermal situation to prolong longer, then it becomes delayed cooking. Longer, time I apply heat, then the oil start forming coke, right? Flexi coking is a more recent one which optimizes the production of the liquid product and minimizes the coke formation, right? We will see them. Then comes the catalytic cracking, hydrotreating. Hydrotreating is essentially just give a treat with hydrogen, right? Hydrogen will probably, remove any unsaturation, right? Hydrogen will sit over the double bond, triple bond and saturate the hydrocarbon. And catalytic reforming. Reforming is converting a paraffin into naphthalene into aromatics. Like hexane is converted into cyclohexane, and cyclohexane becomes benzene, right? So that is catalytic reforming, right? And catalytic cracking, break a long chain hydrocarbon into small chain, right? Hydrocracking means cracking in the presence of hydrogen. Break a long chain hydrocarbon into small branches and don't let it do it in the presence of hydrogen. Hydrocracking. Then comes catalytic dewaxing. So dewaxing, wax is not desirable in the lube oil, so the wax must be, so the lube oil must be dewaxed, remove the wax, right? Catalytic dewaxing may be done. Then alkylation adding alkyl group, right? Then polymerization, small hydrocarbon forming a larger hydrocarbon. Then comes isomerization, right? Where you have, let's say, the same molecular formula but different stereo structures, right? That is your isomers. Okay. Another way of classifying the refinery operation is, see, this is one way we saw. We can break the refinery operation into physical processes and chemical process. Physical processes are all given here. Chemical processes may be thermal and catalytic. I have my thermal and I have my hydrolytic. Right. One more way of looking at it is uh, convert these operations into various headings. Separation process. Separation means something is being separated from something else, right? Desalting, the separation, because you are removing the salt. Atmospheric distillation, you are removing different fractions from the atmospheric column. It's also known as a topping column. Then vacuum distillation and solvent deasphalting, right? So vacuum distillation is a separation process, and solvent deasphalting is also a separation process, right? Because the product which has got asphalt, I am using a solvent to absorb the asphalt so that my other part of the hydrocarbon will not be spoiled, right? Then comes conversion process. Conversion process may be thermal or catalytic. Thermal processes are thermal cracking, thermal visbreaking, thermal coking, as well as catalytic processes, conversion processes. Where is it? So the conversion processes include thermal conversion, which is thermal cracking, visbreaking, coking, as well as catalytic conversion processes like catalytic cracking and hydrocracking. Hydrocracking is same as cracking, except that it is done in the presence of hydrogen. So you usually do hydrocracking when you don't want unsaturation. If your product should not contain unsaturated hydrocarbon, it is better to do a hydrocracking so that hydrogen will saturate those unsaturation. Then comes upgrading process. The upgrading processes are catalytic reforming, isomerization, and alkylation. Catalytic reforming, that is, my crude does not contain enough aromatics, so I will now do by chemistry by making a normal hexane, go to cyclohexane and convert cyclohexane into benzene. So catalytic reforming, isomerization, right? So you know what is an isomer, same molecular weight but different structure, right? So I may require, say, branch chain hydrocarbon for certain reasons as compared to straight chain hydrocarbon, right? So in which case I will use a catalyst and do it what is known as isomerization to get the required product. Okay. Then isomerization, then alkylation. Alkylation is adding a alkane over a alkene, right? So you get a longer chain. So I have, let's say, I want a 8 carbon like octane. Octane is, 8 carbon, right? But I have a 4 carbon and 2 different hydrocarbons with 4 carbon each. I can now find a way by which they will react to form a 8 carbon product, right? That is alkylation. Then come finishing processes. Finishing processes include hydro treatment and hydro finishing. Actually, hydro treatment and hydro finishing means using hydrogen complete the final treatment. Then blending. Blending is, I told you, that I have a whole lot of products in the refinery. I need to blend some of them to get the required, quality and specification of the product at which I'm going to market. Okay, now we start with the physical processes, then we will come to thermal, and later we'll take up catalytic processes. So we are now on physical processes where desalting is the first one. Desalting. Although distillation is known as the first process in the refinery, in many cases, desalting should take place before distillation. It's quite clear, because if salt is present, my distillation column performance is going to be affected. So desalting is the first operation. Then salt dissolved in water, brine enters the crude system as a contaminant during the production or transportation of oil to refineries. Right. So if salt is not removed, then you see serious damage can result, especially in the heater tubes. Heat exchanger will get affected due to corrosion caused by the presence of chlorine. And salt in crude also causes reduction, right? And based on that, we can also have a classification. So whatever said that salt is undesirable in the crude, it must be removed. So the three stages of desalting: adding dilution water to the crude. I add more and more water to the crude to dilute it, and I will now be able to dissolve the salt. Or mixing dilution water with crude by a mixture. Right. So instead of adding, I do a mixing. Mixing means thorough stirring. Right. Mixing dilution water with crude by a mixer. Right. And dehydration of crude in a settling tank to separate the crude oil and sediment and water. So sedimentation, settling tank is nothing but a huge tank where you put the oil, and whatever needs to be deposited will all come down. The main function of desalter is to remove the salt and water from the crude oil before it reaches any of the major unit operation. And the desalter removes contaminant from crude oil by first emulsifying the crude oil with chemicals and wash water to promote through contact of the water and oil. Okay. After the oil has been washed and mixed as an emulsion of oil and water, de-emulsifying chemicals are added, and electrostatic field is used to break the emulsion. Now you see, some salt may form a thick emulsion, right, in the crude oil, right, and that becomes very difficult to remove by your normal methods, right? So we need to break the emulsion. We use electrical methods. So this is an example. You can see crude. It's got low water content, not much water, but high salt content. Now that comes here to a emulsifying device where you are adding in some chemicals to make an emulsion of the salt in the solution, and then this emulsion is taken for further, it goes through water, right? And we now have electrodes. Remember, we are doing desalting. Desalting, we are putting, cathode, anode, and joining them by a circuit, and this should be able to break the oil and settle it down. It's already shown in the figure. You can see that the water so the electric desalting, by applying current, I'm able to ionize the salt and make it settle down. Okay. Desalting is a complex mixture that crude oils are complex mixtures that contain a high degree of impurities like water, salt, solids, and metals. These impurities have adverse effect like corrosion, fouling, and until upsets. The main purpose of using desalter is to remove the salts, typically calcium, magnesium, and sodium, to minimize the corrosion. Then we come to among the different types of desalting. Electric desalting is the best. See, if I allow the crude oil to stay in a tank, just sedimentation can deposit. But if the salt has formed a sort of emulsion with the crude oil, then it will be difficult to do it. So my electric desalting is better than the other type, like settling technique and centrifuge separation. It also requires less time and cost. Desalting and dehydration is achieved simultaneously with the spectacular removal of more than 90% of oil from 90% of the salt from the rock crude, right? In just less than half an hour, right? So electric desalting can remove more than 90% of the salt in less than half an hour. That's good enough, great. The principle in the separation is very simple. When a charged field, when under a charged electric field, the polar molecules orient, right? So you see, I'm keeping a potential of 20 to 70 kilovolt is present in the form of emulsion and also coalesces and agglomerates to a stream, entrapping all the solids in the process. Okay, so you can see that desalting is one powerful way of removing the electric desalting is a powerful method for removing the salt in crude. And the brine collects at the bottom of the desalter, which crude floats above and forms a separate stream. Performance of electric desalting depends on key parameters, that is the crude oil properties, desalting, temperature, pressure, pH, residence time, right? Water wash, quality and rate, wash water mixing, and finally of effective separation. So desalting, then after desalting, for effective desalting, required temperature is 120 to 260 degrees C. Pressure should be 5 to 6 kg per meter square, right? And pH. pH is another important parameter in desalting. pH should be this 5.05. Okay, not 505, it is 5.05, right, to 7. Chemical assistance termed as emulsion breaker, right? Wetting agents and our demulsifiers is extremely important by the desalting operations. Okay, so you have the temperatures for desalting is in the 120 to 260, pressure is 5 to 6 kg per centimeter square, pH is 5.05 to 7. Okay, so I may add some chemicals which are termed as emulsion breakers or wetting agents, right? And the power consumption is also very small, frequently of the order of 0.01 kilowatt hour per barrel. Experience shows that that chloride content of the desired desalted crude that exceeds 20 ppm have the potential of leading significant corrosion and during fouling issue in the overhead lines. Then, now that we have done with desalting, then we come to distillation. So you agree that crude oil is a complex mixture, right? So once desalting is done, now we go to distillation. Distillation separates the hydrocarbon compounds into distillate fraction based on their boiling point or volatility. More volatile compounds, more volatile means lower boiling point, tend to vaporize more readily than heavy compound. And this forms the basis of separation through distillation. Right. So this is the basis for distillation. You'll be learning more in the advanced mass transfer course later, right? But now keep it that more volatile compounds tend to vaporize more readily than heavy compounds. So in fact, volatile means vaporizing immediately, right? In a distillation column, light compounds are removed from the top of the column and the heavier part of the mixture appears in the bottom. Remember, distillation column separates it based on the volatility or the boiling point difference. So the lighter ones are on top, the heavier ones are at the bottom, right? So for a crude, that is a mixture of thousands of hydrocarbons. Some very light compounds such as ethane and propane may appear in the top product. So I may at the most get, say, some methane, ethane, or ethane, propane, right? And extremely heavy and non-volatile compounds such as asphalt will appear only in the bottom. See, the lightest component found is, what is this, referred as overhead distillate or full range naphtha, and is sent to the light end unit for further separation into LPG and naphtha. Then comes the side stream or separated. We are coming to the picture next, just hold, right? Into atmospheric distillation gives fractions like straight run, kerosene, light and heavy. Then the residue from the atmospheric distillation column generate two side streams, light and heavy vacuum gas oil and vacuum residue from the bottom. All these distillation products are subject to subsequent processing to produce light and medium middle distillate fuels and non-fuel products. So look at the crude oil, desalting. So some water is added. Why do we add water? The reason for adding water is to remove the salt, because salt will be more preferred in the H2O than in crude oil, right? So you know the solubility criteria. Then the desalted crude enters into the atmospheric distillation column, which is also known as the topping column. So you can see somewhere entry and here is the exit. Now, what are all we are getting? Remember, the crude that is coming is actually having compounds of many kinds with different boiling point ranges. So in the distillation, the lighter ones come on top, overhead distillate, right? Then comes full range naphtha. Then comes kerosene. Then lighter gas, heavy gas oil, light gas oil. So overhead distillate, kerosene, light gas oil, heavy gas oil. Then the bottommost product is atmospheric residue, and this enters into the vacuum distillation unit. Okay, so this is in a nutshell, right? So you can see the overhead distillate, they may also go inside to improve the quality. Okay, but desalting is must. After desalting, it enters into the atmospheric distillation column, also known as the topping column. The residue from atmospheric distillation, when it may give leak out gases which are, where is this? The lightest product will be light vacuum oil, light vacuum gas oil, typically boiling point 690 to 750 degree F. Then heavy vacuum gas oil, then vacuum residue, right? Then come the light end units, because remember, this has to go through some more changes. So you can see the light end unit. Where is this? Full range naphtha. Full range naphtha undergoes debutanizer, means it will remove the butane, right? And then, so you got no C4 and lighter compound, which goes for what is this? One more separation. C4 and lighter means I'm having both ethane as well as propane. So I now put into another separation distillation where I'll get C3 and lighter and C4 here. That is the separation involved. And the debutanized naphtha means butane has been removed. So the debutanized naphtha goes for naphtha fractionator. Then de-ethanizer unit. What all is happening there? Right. Then what is C4? C4 is butane. Now you see butane from the depropanizer, right? Butane from the, here is butane, right? Butane is separated here. C3 is here. Butane, that is a D-butane, which is from the depropanizer. It goes along with propane, then sweetening removes the sulfur and essentially H2S in the production of this form liquefied petroleum gas, LPG. Right, LPG is nothing but a mixture of propane and butane. So the C3 and lighter may go through another column to remove ethane and the lighter compound. So like this, we can go on more separation. This is only a idea giving one. Okay. Then you come to debutanize naphtha from the debutanizer. Debutanized naphtha. Debutanized naphtha. Because butane and all have got removed here. So what happens to the debutanized naphtha? Right. It goes through naphtha fractionation. Fractionation means deriving many fractions. Right. So I get C5, C6 light iodide paraffin and gasoline blending pool. This I may use for blending in my gasoline blending station. Then comes propane deasphalting. Okay, propane deasphalting. Where is this? Remember from the vacuum column, the asphalt is nothing but tar-like substance, right? So my atmospheric distillation residue goes for vacuum distillation. That is the bottom product of atmospheric unit is my input to vacuum distillation unit. So in vacuum distillation, I get three fractions: light vacuum gas oil, heavy vacuum, and vacuum residue. Right. So this is done 10 millimeter mercury. That is in vacuum condition. See, why vacuum is the sense that the separation becomes easy, right? The partial pressure is lower, right? And these are some of the advantages of doing in vacuum, right? And I have light vacuum gas oil in this boiling range, heavy vacuum gas oil in this range, vacuum residue in this range. Then it goes for a light end unit. Where is this light end unit? Yes, here. This goes for light end unit. Light end unit consists of a sequence of distillation process to separate the overhead distillate from the product distillation column into 5 streams consisting of methane, ethane, propane, butane, light naphtha, and heavy naphtha. All these are there, right? Then the fraction C2 and lighter, C2 is what? Ethane, right? 2 carbon. And lighter means maybe methane, right? The use as a fuel gas in the refinery to provide heat or generate steam. Then propane and butane is sold as liquefied petroleum gas LPG after sulfur is removed, and light naphtha fraction that contains C5 and C6, that is basically pentane and hexane, is sent to the gasoline blending pool as straight run gasoline, while the heavy naphtha fraction Heavy naphtha is rich in cycloalkanes and naphthalene, is sent to a catalytic reforming process to produce gasoline with high octane number. Then we have seen this, right? This full range naphtha becomes C4. This is a series of separation. Now you remember why we studied in process synthesis the separation sequence. Now I am applying them to generate these flow sheets, right? So my feed contains so many, I am removing step by step each stage, right? Then propane deasphalting. So remember, from the vacuum distillation unit, the product may contain asphalt. And asphalt is a dark tar-like substance which is not desirable in the hydrocarbon products which we have. So asphalt must be removed. That is why I'm using the word de-asphalting. How do I remove it? Right, when asphalt is there, coke forming tendency increases. This must be removed, reduced by removal of asphaltenic material, large aromatic compound by means of extraction. So liquid propane is the solvent which is widely used, but of course I can use butane and pentane also, but liquid propane by and large is the most used solvent for de-asphalting. So that petroleum fraction which contains asphalt, I will mix it with propane solvent. Propane will absorb the asphalt and the remaining will go away. And by heating the solvent, I will now get my solvent and asphalt separate. So propane deasphalting is based on the solubility of hydrocarbon in propane, that is on the type of molecules rather than molecular weight as in distillation. So here is that in this propane deasphalting, it is a type of molecule which matter, not the molecular weight of the compound. Propane deasphalting, I'm just showing a scheme. It is a typical solvent extraction process. Remember, solvent extraction is one of the main operations in the refinery, right? The feed, which is a vacuum residue, right? The bottom of the vacuum distillation unit is vacuum residue. It goes for deasphalting and is contacted with liquefied propane counter currently, right? Counter current operation, you know the advantage. Alkynes that are present in the field dissolve in the propane, whereas asphaltene, the coke precursors, do not dissolve. Right. So what happens is in the propane, the alkanes, right? The alkane will dissolve in propane, whereas asphaltene will not dissolve, right? So asphaltene will pass through, and then by evaporating the propane or depressurizing it, I can remove the alkane. The remaining de-asphalted oil is stripped with steam to remove any residual propane, and the asphaltenic material may undergo similar treatment. The asphalt residue may go for thermal processes such as disc breaking, delayed coking, flexi coking, etc. It may also be processed in a hydro processing plant. Many options are available. You can see the vacuum residue is input for propane deasphalting, right? And where is the propane coming? Yes, the vacuum residue comes from top to bottom, and the propane goes from bottom to top, right? And then you have a propane evaporator, right, which will now be regenerated and brought back, right? You can see the complete regeneration of the propane. Any loss is gone, make a propane and refed. So vacuum residue and propane goes through a regeneration by boiling, removing the dissolved hydrocarbons. Okay, so you now have the deasphalting tar. This goes for flashing, right? That is the release of pressure, and that also removes some propane, which is brought back, and asphalt is removed. and you have the deasphalted oil. So propane deasphalting is a very crucial step. Okay, then solvent dewaxing. Remember, the lubricating oil cannot contain any wax because wax will clog the machinery where the lube oil is applied. So solvent dewaxing is done. Usually it is done by methyl ethyl ketone or propane as solvent for removal of naphthenic and aromatic compound. Furfural or phenol may be used as a solvent. So dewaxing may be done by MEK, methyl ethyl ketone or propane, and naphthenic and aromatic compound. They don't have good properties in the lubricating oil. I may use furfural as a solvent or phenol as a solvent to remove the naphthenic and aromatic compound. So propane deasphalting, solvent extraction for naphthenic, aromatic, and solvent dewaxing form the lube oil processing. Remember, lubricating oil is a big lucrative business of the refinery, right? So you have the distillation, then vacuum distillation, then deasphalting, solvent extraction for removal. See, remember, deasphalting we already saw, right? Deasphalting, propane deasphalting, right? Propane deasphalting, then solvent extraction, maybe using furfural or phenol for removing naphthenic and aromatic compound. Then goes for solvent dewaxing. I may use methyl ethyl ketone as the solvent, and then goes for finishing. And then I have the lube oil ready for my marketing and blending. Right? You can see that typically carbon 26 to carbon 40, C26 to C40 hydrocarbon or what is paraffinic hydrocarbon are good ones for the lube oil. They have long carbon chain and a high resistance to oxidation. Remember, lube oil cannot get oxidized. It must withstand oxidation. Otherwise, you will have a mess in your machinery. Right? Your lube oil gets oxidized means your machinery will go into a problem. Right? So lube oil should not get oxidized and it must have a good high pour point. Right? You know what is pour point? High viscosity. I mean, it should be thick. Right? Low volatility and low specific gravity. These are some of the requirements for the paraffin, whereas naphthalene have multiple carbon rings, they're like cyclohexane and big chain, medium resistance to oxidation, low pour point, low viscosity, high volatility, high specific gravity, and similarly aromatics also are not stable and so they are undesirable. So naphthalene and aromatics must be removed by solvent extraction using furfural or phenol. And deasphalting is done with propane, and solvent dewaxing may be done with either methyl ethyl ketone or propane. Right? So you can see more details about lube oil processing in this what is that reference that is given there, right? And then solvent dewaxing we have already seen, right? Solvent dewaxing is using this either what is this methyl ethyl ketone or propane because wax compounds cannot be there in the lubricating oil. It must be removed, right? The wax must be removed. I can use propane or methyl ethyl ketone, and methyl ethyl ketone has superior solvent properties as compared to propane, right? Sorry, propane as a solvent as compared to methyl ethyl ketone. So propane may be more used than MEK because the propane is both a diluent and a refrigerant. It is lower capital investment, refrigeration energy saving, higher filtration rate, rejection of asphaltenes and resins, higher what is that viscosity index than ketone dewaxing. Right, viscosity index means higher viscosity. Right, so you can see that propane is a superior solvent for dewaxing as compared to methyl ethyl ketone. So this is a schematic of the dewaxing operation, right? I have, where is my, this is the finished product, right? I now have my uh, product, they are at lower temperatures, right? And the solvent and water, right? So it goes through a filter, oil and solvent. So the wax and solvent goes for a change, right? The solvent is removed, and I'm using steam wherever heating is to be done, and the purified oil comes into the base stock, right? So wax content is to be removed from the lubricating oil before it can enter blending and marketing purposes, right? Then we have the thermal processes. I'll take a few minutes to wind up the thermal processes. I have, uh, hello, I have the thermal processes where I have wisp breaking, delayed coking, and flexi coking. These are basically chemical changes using heat, right? So thermal processes are flexible, but a disadvantage is that a lot of low value products are formed. That is why some improvement like flexi coking has all come into place. It is similar to the operations are very simple application of heat. Wisp breaking. Wisp breaking, you can see, just put a heater to heat the vacuum residue. The vacuum residue goes through heating, and by heating, I am reducing the viscosity, right? And then goes for distillation separation, where one product I get is gasoline, and another product I get is light gas oil, and then this what do you call the settling brings me into a vacuum fractionator where I get heavy gas oil and cracked residue, right? So this breaking gives me a small improvement in the yield of gasoline, but I still end up forming a lot of this cracked residue and all may not be suitable, right, for further improvement of properties. Okay, so this is just the application of heat. So by applying heat, I am reducing the viscosity, and now I am doing fractionation to do it. So this is your wisp breaking. It is done at 710 to 760 degrees, and reaction time is 1 to 8 minutes, very short time, and 10% only of the vacuum residue, only 10% can be got as gasoline. Remaining 80% is cracked residue, which is a very low product, only used as fuel. Right? So, this breaking is not a very economically good one for production of gasoline. Right? Remember, I am trying vacuum residue, which is a kachada from the refinery, into small 10% of gasoline I have recovered from it, because this has got more market value than this. Right? Delayed coking. Mean if I carry out the thermal treatment longer and longer, here I am doing just for 1 to 8 minutes. If I do it longer and longer for several hours, all my hydrocarbons will all get smashed up and end up forming carbon, that is coke formation, which is similar to how the coke oven battery operates, right? So you can see my heavy feed, it will give me three products, some gaseous product and some liquid product and petroleum coke. Petroleum coke may be used for making anodes and cathodes, electrodes for the electrochemical industry, right? So severe wisp breaking is delayed coking, right? This similar coke is similar to the refractory coal and is used as fuel in power plant. And the original goal of delayed coking was minimization of the output of residual oil and other higher molecular weight material. But over the years, it was found profitable to produce certain types of coke. A good example is the production of coke for electrodes, which is in fact the largest non-fuel end use of petroleum coke, right? So carbon anodes, coke is carbon, right? We have a small flow sheet to see the delayed cooking. See, delayed cooking is only protracted. So my vacuum residue is entering the fractionator, right? And I get a gas oil and as a bottom product, and the top product is recycled back into the fractionator, and the top one, I again separate it into gas and naphtha. Small quantity of naphtha is produced, and here my bottom product from this fractionator goes for furnace, that is very severe heating, and from there it goes to the coke drums. The coke drums, is where the ultimate carbon formation happens. It is done at 710 degree K and 2 atmosphere pressure, right? So you can see that it is entering at 770 and coming out at 710, right? So I have, remember, just go through the sequence. The vacuum residue goes here, right? And here you have a small quantity of gas, naphtha and gas oil produced, and the bottom product of the fractionator goes into a furnace and stays in the coke drum for prolonged hours. See, there are two coke drums. When one gets saturated, when one gets filled up, it has to be emptied. So the other one is switched over, and this is emptied. And when this is full, by then this will be empty. So this to do a continuous operation, you have two coke drums. One when one is operating, the other is waiting, right? And when this is full, the operation will be switched over to this. Okay. Then comes flexi coking. Remember, whisk breaking and delayed coking are two extremes. In whisk breaking, I could just get 10% only I could recover as gasoline. And in delayed coking, I'm ending up producing more coke, right? And I'm not getting much slight improvement than the whisk breaking, but still not enough. So flexi coking is the way by which we improve the gasoline. Remember, the refinery's main goal is to produce as much petrol as possible because that is where the market and money lies, right? So what is done in flexi coking is we don't make coke as a product, but we will use coke to undergo some steam reforming reaction or partial oxidation to produce hydrogen, carbon monoxide, carbon dioxide, methane, etc. What a beauty, right? So coke, that can undergo with partial oxidation, it will form carbon monoxide and hydrogen, right? And with the steam, it will form also carbon monoxide, hydrogen, and some methane, etc. So I am using now to produce particles, my coke formation is minimized as little as possible, and I maximize my gas product output. So that comes into the flexi coking, which is a superior one, which is of more recent. You can see that my input is here, right? And done at 1200 to 1300. Steam and air is mixed because I want this reaction to take place, right? And then it goes into a heater, and from the heater it goes into separation, where from the separator some coke slurry is removed, and I again go into a fractionator. See, the vacuum residue enters here. Just starting here, is a integrated one. So the vacuum residue, you get liquid product for fractionation, and then the bottom product comes to the heater, and here is a gasifier. That is remember that we are trying to incorporate this reaction into the operation, and the sulfur-rich gases may be separated for sulfur removal also, and I get coke gas which can be used as a fuel. So flexi coking, imagine, can recover about how much? Almost 80%. Coke constitutes approximately 30%, 38% of the cracking product, right? So the coke particles are transported, so I improve my overall yield of the gasoline high value product in flexi coking. So these are the operations which are there in the refinery, physical, chemical. Today we have had a run through of the physical processes and the thermal processes. Tomorrow we will take up the catalytic processes, right? Hydrotreating, catalytic reforming, etc., right? And the slides for today's lecture, I put it up in the Google class, and you can go through it. And you could see another flow sheet of the refinery where I have my atmospheric distillation. The bottom comes to vacuum distillation, propane deasphalting, right, and solvent extraction and solvent dewaxing, and then treatment blending and removing coloring substances. So I have my lubricating oil product, and this whole chunk this whole chunk is full of catalytic processes, cracking, isomerization, alkylation, and reforming. And this, today we have seen mostly this part of the refinery, that is the atmospheric distillation, vacuum distillation, solvent extraction, lube oil processing, etc. But the main chunk of the refinery is in the catalytic processes, which include cracking, reforming, isomerization, sulfur, alkylation, polymerization, etc. We will come to that. Okay, so we will catch up tomorrow. Thank you all. Thank you. Thank you. Thank you.
Thank you, sir.